Welcome to lecture 19 of Unit 2, higher order ODEs. So today we're looking at an application of higher order ODEs, and that is going to be the spring mass system. Okay, we're going to look at three different cases of the spring mass system throughout the next few lectures. Okay, so this idea that we have a spring and a mass attached to that spring, and the spring can be oscillating up and down. Of course, this almost feels like a toy system, but in fact, the same system of equations is applicable to things like RLC electrical circuits. So if you know anything about basic circuit design, you'll know what an RLC circuit is. But it's also applicable to other areas such as in particle mechanics, where you have particles interacting with one another through forces pushing into each other. They have a sort of like a spring-like resistive force as well. So even the spring mass system is quite a good test case to look at an application of a second-order linear ODE. So the idea is fairly simple. We have a spring with a mass. This ball at the bottom is a mass. Perhaps we extend that spring and then just let it oscillate up and down, okay? And we're going to look at three different situations for this system. Okay, before we get into the equations, we need to define a few things first. Okay, so the first thing I want to define is this little cartoon drawing here. This is just the spring which is hanging from a roof with nothing attached at the bottom. So there's no mass on the bottom here. So if we do that, the spring just has a natural length or an unstretched length, which I'm going to call L, okay? But as soon as I add a mass on the bottom of that string, so I add some weight to this spring, obviously the spring extends a little bit. Okay, and the length that it extends is this distance S, okay? Okay, so this extension is length S. So now with this spring and the mass attached to the bottom of the spring, the equilibrium position, the position where the spring is extended but it's not moving anymore, is called the equilibrium position. Okay, and this is at the length of the spring plus this extension due to the mass. So L plus S is the equilibrium position for this mass spring system. Okay, but if we extend this spring even more, let's say we grab the mass and we just start pulling it down, then we can extend the system even further, and we're calling that distance X. Okay, so I've pulled this spring down a further distance X. Okay, and so the motion relative to the equilibrium position, which was L plus S, the motion, or let's say the extension, I should say, relative to the equilibrium position is called X. Okay, so X can be equal to 0, of course, but it can also be positive or negative. And in fact, we're going to define X to be positive when the spring is extended, okay? So basically, X is positive moving down here, because we're extending the spring, we're making it longer, so I'm going to define X to be positive. If you did this the other way around, and you defined X to be positive going up, then you'd get similar equations just with a sign change. Okay, but the point is, in this system here, X is going to be an extension, so it's positive when we're extending the spring, it's negative when we're compressing the spring, okay? So this spring we may extend it here, and then it will, obviously due to the force of the spring, bounce back up here, so it may come past its natural length. And then X will be negative. Okay, so the force is acting. There's a little bit of a physics slide to the lecture today, but the forces acting on this system, on the mass, are the weight force due to gravity and the spring restoring force, which, if you've taken any, well, let's say high school or first year physics class, then you know that this is governed by something called Hooke's law. Okay, so if we start with the gravity force, or the mass, the weight force due to gravity, F1, so our weight force is equal to the mass of the spring times gravity, where gravity on Earth is 9.8 meters per second square. So this is some acceleration, the acceleration of gravity on Earth. Obviously, this is different if you were on the moon. It's asked Neil Armstrong. And then the Hooke's law. Hooke's law tells us that the force due to the spring, the resistance of the spring, is equal to negative some constant k, which we call the spring constant, times the extension of the spring past its natural length. Okay, so the spring that's been extended, firstly, one, because of the weight, so it's been extended a distance s because we've put a weight on the end of the spring. So there's some force that the spring applies to resist that. And then also, if we pull that spring down even further, we have some extension x. Okay, so the restoring force, the spring's force due to Hooke's law, is just negative k spring constant times the extension past the spring's natural length. Okay, and that's what I said here. The negative sign basically is because the force is, if we stretch the spring, if we pull the spring down, the force is going in the upwards direction, which we said is the negative x direction. So that's why this negative comes out here in front of the spring constant. Okay. So these are our two forces acting, or at least the two that we're considering at the moment, acting on our system. And at the equilibrium position, x equals 0, the forces F1 and F2 have to balance, because if the spring is not moving at all, then these forces have to be in equilibrium. So the sum of those forces has to equal 0, okay? So when x equals 0 at the equilibrium position, the sum of these forces, F1 plus F2, has to equal 0. And so that's what this equation here is, okay? K and S are constants here. K is the spring constant, and S is the, if we just put, S is the distance that, if we just put the mass on the end of the spring, S is the distance that spring extends. Okay, so K times S is a constant here. So what I can do is add K times S to both sides, and then I find that the value of Ks is just equal to mg. Okay, so if I add Ks to both sides, Ks equals mg. So I in fact can simplify my expression for F2 here, because I have a K times S, which I now know as mg. So now I can rewrite my force F2 as F2 equals negative Kx minus mg. Okay, so then if we look at the sum of F1 and F2, it's quite interesting because the gravity term cancels out, in fact. Okay, and we'll come back to that shortly. But we also have other forces that may be acting on our spring mass system. Okay, firstly, we may have damping forces due to friction or air resistance. So obviously, being on Earth, there's always going to be some friction and air resistance present. And so we can express that force using this expression here. So negative beta, where beta is some constant, dx by dt, okay? Beta is called the damping constant, and that has to be greater than 0. Dx by dt, well, that's just the rate of change of the position with respect to time. So that is just the velocity of the mass as it oscillates up and down on the spring. Okay. Again, the sign is negative because the damping force opposes the direction of motion. So if our spring and mass system is moving down, so extending the spring, then the force due to damping is upwards. So again, that's just where the negative sign comes from there. There can also be external forces, such as, well, for example, when we pull the spring down, or let's say every time the spring, well, if you think about it like a swing, a similar thing, when you're pushing a child on the swing, they swing forward, they swing back, and you push them again. And they swing forward and they swing back and you push them again. So you have some external forces. You could do the same thing for a spring. Every time let's say it gets extended, you could just give it a little tap upwards as well. So you can have external forces on a system like this. And so we're just going to call that force F4, or just some function f of t, because this can be anything we decided it's going to be. Okay. But at the moment, this is just some general function. some general force that we can apply to the spring. Okay. So using Newton's second law, we can define a second order ODE to describe the motion of the system. Okay. Okay, so we know from Newton's second law that the sum of all forces acting on a system, so that's what this sigma F is here, the sum of all the forces is equal to the mass times the acceleration, okay? Now the acceleration, we can write that as the second derivative of position with respect to time, right? So here we really have, A here is a second derivative of x with respect to time. We have our four forces that we've described here. We've got the force due to gravity. We've got the spring resistance force, or let's say the Hooke's law. We've got some damping force here, and we've got some external force that could be present. Okay, and so what Newton's second law says is we have to add all those four forces together. And again, notice if we do that, F1 plus F2, the gravity term is actually going to cancel. So if we do that, we end up with mass times the second derivative of x with respect to t. So this was this acceleration term here. So that is that's where this comes from. Plus beta times dx by dt. So that's from force 3. So the damping force. See, we had a first derivative of x with respect to time. Plus k times x. So that's Hooke's law. So this is F2 over here, equals some external force. Okay. So this is the ODE that governs the behavior of a mass spring system. Of course, you can see that this is a homogeneous second order linear ODE with constant coefficients. So we know how to solve this. We've solved this a few times in this class already. But a few notes though. If we do not have an external force, so if that right hand side f of t equals 0, then we say the motion is in free motion, so we have free motion. If beta equals 0, then we say the motion is undamped. Okay. So for example, we may be given an initial value problem here, and we're told that this represents a spring mass system. So what we might like to do is interpret each of these terms in this equation here. Okay, well, the mass is equal to 2 kilos, so the mass on the end of the spring is equal to 2 kilos. That's just the term which is multiplying the second derivative. The spring constant itself is 3 newtons per meter. Okay, I don't expect you to know the physics units for some of the more complicated things. Well, okay, I expect you to know the units for mass, but and maybe things like time. But it's always good if you can to include the units. Okay, so the spring constant is 3 newtons per meter, so that's the 3 is the number that's multiplying the linear term x here. Beta equals 1.5, so beta is the damping coefficient that's multiplying the dx by dt term, the first derivative term here. And there is a periodic external force on the system, which the force is represented by 5 times cosine of 4t. Okay, so that is the interpretation of each term in this ODE. But what about the initial conditions though? Well, the mass is released at 0.5 meters below its equilibrium position. So at time t equals 0, x of 0, time t equals 0, the mass is at 0.5, we'll assume meters. So that's 0.5 meters below its equilibrium position. We've extended that spring by ½ a meter. Okay, it must be a big spring. Okay. The initial velocity, so x prime is the velocity, dx by dt, at time 0 is equal to -1. And well, let's say it's meters per second. And so because it's negative, we know that the velocity is upwards. So we're releasing this spring ½ a meter below its stretch position with an upwards velocity of 1 meter per second. So it's a big spring and it's traveling fast upwards. And we know it's going upwards because we defined x to be positive in the downwards direction, in the spring extension direction. So because we've got a negative initial velocity here, we know that it's initially traveling upwards. Okay, so let's look at three specific cases here. We won't get through them all in this lecture, but I think we'll get through two. So case one is what we're going to call free undamped motion. So free meaning that f of t is equal to 0, and undamped meaning that beta is equal to 0. Okay, so if these two terms, the beta term and the f term, are 0, we just get left with mass times the second derivative of x with respect to time plus k times x equals 0. Okay, and I can simplify that by dividing through by the mass here. So if I divide through by the mass, I get the second derivative of x with respect to t plus k over m times x equals 0. Okay, and here I'm just calling this ratio k over m, I'm just calling that omega squared. Okay, it's just a name. We can call it whatever we want, but I'm just calling this omega squared. You'll understand why I say squared soon when we solve it. But I guess one point is we know this is positive because the spring constant has to be positive. The mass has to be positive. So, well, we know that omega and omega squared have to be positive. Or at least we know that omega squared has to be positive, Okay, so this is our ODE, our second order ODE here. The equation describes something that you may have heard of, which is called simple harmonic motion. And so here we're just calling it free undamped motion, but it's the same thing as simple harmonic motion. Okay, well, we can write down the auxiliary equation for the second order ODE. We're going to get an m squared term here plus omega squared equals 0. And we can find the roots to that equation, and it turns out that they are imaginary. In fact, complex conjugate roots, right? There is no real part of these roots. They are purely imaginary. And so hence we can write down, because we know how to solve these systems now, these second order constant coefficient linear systems, we can write down the solution x of t equals c1 times the cosine of omega t plus c2 times the sine of omega t. So maybe you realize why I called this k over m, I called that omega squared. I really only did that because when I get my solution, I avoid having anything like a square root of omega. Having the squared means I just get omega down here rather than some square root of something. Okay. So this solution here is the solution to the simple harmonic motion equation, which we've got up here. So this is when the spring has no external forces and no damping. But this is not the way you've probably seen the simple harmonic motion equation displayed to you before, right? So if I introduce my solution up the top here and just give myself a bit more space, we know that from physics we can write the simple harmonic motion as x of t equals a times sine of omega t plus phi, okay? A is some real number, a is positive because a here is what we call the amplitude of the motion. Phi is going to be something called the phase angle too. Okay, so we know that, well, we know from solving the ODE that we get this sum of cosines and sines up here, but we know from simple harmonic motion that this must be equivalent to this expression amplitude times the sine of omega t plus phi. Okay, so how do the two solutions relate to each other? Let's find that out. Well, we have the trigonometric relation sine of the, well, in this case we're interested in the sum of two angles. So let's just say the sine of the sum of two angles equals sine of one of the angles times cosine of the other plus cosine of the angle times sine of the other. Okay, so we can apply this trigonometric relation to this sine of omega t plus phi, and that allows us to write x of t equals a times sine of omega t times cosine of phi plus a times cosine of omega t times sine of phi. Okay, and you should be able to see here that these two are equivalent, because here we've got a cosine omega t, here we've got a cosine omega t, here we've got a sine omega t, and we've got a sine omega t here. So it's not too hard to point out that C1 here is equal to A times sine of phi, and C2 is equal to A times cosine of phi. Okay, so if we define C1 to be the amplitude of the motion times the sine of the phase angle, and C2 to be the amplitude of the motion times the cosine of the phase angle, then these two representations of the solutions are equivalent. Okay. And so we can find the constants A and phi just using basic trigonometry, right? Okay, so A I'm going to claim is equal to C1 squared plus C2 squared square root of this, right? And the reason that is, if you look at the sum of C1 squared and C2 squared, well, we get A squared sine squared phi plus A squared cosine squared phi. We can bring out the common factor of A. Sine, then we be left with A times sine squared phi plus cosine squared phi, which we know is equal to 1. So we end up with A squared, and then if we take the square root, we just get A. Okay, so the amplitude of the motion is just equal to the sum of the squares of these two constants, C1 and C2, and then the square root of that. However, the phase angle phi, there are multiple ways we could calculate that, right? So we could invert this equation C1. I could say C1 divided by A equals sine of phi. So that's where I get here, sine of phi equals C1 divided by A. Similarly, I could say, invert the second equation. I could divide through by A and say cosine of phi equals C2 divided by A. So that's this bottom equation here. Or I could divide C1 by C2. The A's would cancel, and I just get sine phi divided by cosine phi, which is tangent of phi. So tangent of phi would be C1 divided by C2. So I get three ways to calculate phi. We have to check that these are equivalent ways to calculate phi, but I think we'll come back to that soon. Just again, A here we said is the amplitude, phi is the phase angle. This thing omega, which remember omega squared was k over m, so omega is the square root of k over m. That's measured in radians per second. This is called the angular frequency. And if we take the angular frequency and we divide it by 2 pi, then we get something called the natural frequency. Okay, so this is measured in cycles per second. Okay. This is just all this information that we just have on the last slide. I just needed to make a bit more space because if we invert the natural frequency, so 2 pi divided by omega, which is measured in seconds, this is the period of the motion, okay? So it's the time it takes for one full up-down cycle of motion. Okay, so this is the information that we need to know about simple harmonic motion, or what we were calling free undamped motion. The spring mass system will oscillate forever because we have no damping forces, so this is not a particularly realistic situation, but it's a good place to start when we're learning about the spring mass system. Okay, so I want to look at an example before we move on to case 2. So let's look at this, what I'm claiming is a spring mass system. Second derivative of x plus 64x equals 0 with some initial conditions. So I'm starting the motion at time equals 0 with the spring extended 2/3, well, let's say a meter, 2/3 meters below its equilibrium position. Its velocity x prime at time t equals 0 is -4/3 meters per second. So it's moving upwards at time t equals 0. There's no external force, there's no damping force here, so we're expecting some kind of simple harmonic motion, some free undamped motion. I can identify omega squared equals 64 because this is the, I must have divided through by the mass already here because there's nothing multiplying the second derivative term. So omega squared equals 64, or you could say that the angular frequency is 8 radians per second. You could say the natural frequency is that 8 radians per second divided by 2 pi, so 4 over pi cycles per second. And we could measure the period there to be the 1 divided by the natural frequency, so 2 pi divided by omega. So that is pi over 4 seconds. So that pi over 4 seconds is how long it takes for this spring to complete one up-down cycle. Okay, and we also know that the ODE has this solution here, C1 times cosine of 8t plus C2 times sine of 8t. And we can find those constants C1 and C2 using the initial conditions, right? Okay, so if I take the first derivative of our solution, x of t here, well, I get the cosine becomes a negative sine, and we bring out this 8 here, so I get negative 8 C1 sine 8 of t. The sine becomes cosine with no sign change, and the 8 comes out front, so plus 8 C2 cosine 8 of t. And then I can sub in my initial condition. So my initial condition on x, when t equals 0, I get C1 times cosine of 0, which is just 1, plus C2 times sine of 0, which is 0. So I just get x at time t equals 0 is C1. And my initial condition was 2/3, right? X at time t equals 0 is 2/3. So C1 equals 2/3. I can look at my initial condition on the velocity, so x prime. I can sub in when t equals 0 there. Well, this first term is 0. The second term is just 8 times C2. And that has to equal my initial condition on the velocity, which is negative 4/3. So if I divide through by 8 there, I get quite simply that C2 equals minus 1/6, C1 equals 2/3. Okay, so let's use C1 and C2 in the ODE solution there. So here my C1 2/3, C2 negative 1/6. And let's try to identify the amplitude of the oscillation there. Okay, so amplitude is C1 squared plus C2 squared. So 2/3 squared plus minus 1/6 squared, square root of all that of that sum. And we get, well, if we do that, we get square root of 17 over 6 meters. Okay, so this is the amplitude of the oscillation, the distance from the bottom of the extension of the spring to the top. Okay, but what about the phase angle phi? Because as I said before, there were 3 different ways to calculate that phase angle. We could either calculate C1 over C2, the inverse tangent of that, the inverse sine of C1 over the amplitude, the inverse cosine of C2 over the amplitude. And the question is, are these 3 ways to calculate phi equivalent or not? Okay, well, let's try it out. Well, phi is equal to the inverse tangent of C1 over C2, which is about 1.3 radians, or the inverse sine of C1 over the amplitude, which is about 1.8 radians, or the inverse cosine of C2 over amplitude, which is negative 1.3 radians. So in fact, here we get 3 different solutions, and at the moment we don't know which one is correct. Okay, we get 3 different solutions because, of course, the sine and cosine are periodic functions and they are offset by 90 degrees, right? So for our system, we need to figure out which one of these phi, these phase angles, is actually correct. Okay. So firstly, let's note that C1 is 2/3 is positive, and C2 is minus 1/6 is negative, okay? Sine of phi is equal to C1 over alpha, over A. A is the amplitude, which is always a positive. So if C1 is positive and A is positive, that means that the sine of this angle phi has to be positive as well, okay? Because sine of phi equals the ratio of 2 positive things, so it must be greater than 0. And similarly, the cosine of phi is C2 over alpha. Alpha is positive, C2 is negative, so this ratio is negative. So that means that the cosine of this angle phi must also be negative. Okay. So our thing we're noticing here is that whatever this phase angle phi is, the sine of that angle phi has to be positive. The cosine of that angle phi has to be negative. Okay, well, let's plot these two curves. We've got sine in red here. We've got cosine in this dotted blue line here. And so let's look for regions where sine is positive. Okay, so sine is positive between 0 and pi. Let's look for regions where cosine is negative. Cosine is negative between 1/2 pi and 3/2 pi. And so there is one region that satisfies both of these conditions, and that is this scribbled green region here between -1/2 pi and pi. So here in this region, sine is positive and cosine is negative. Okay, so we know that our phase angle phi has to be between these two numbers, pi over 2 and pi. If I just write that in terms of numbers, pi is of course 3.14 something. Then we know that phi has to be in this range here, 1.57 to 3.14. Okay. Is there any value of phi that satisfies that out of these three potentials? 1.3 is too low. Negative 1.3 is negative, so we don't want that. But 1.816 is perfectly between these two values here. So our phi, we've concluded, is 1.816 radians. So hence, we can write our solution like so. The amplitude times the sine of omega t plus phi. Okay, well, omega was 8, so we can add that in there. X is equal to the amplitude was square root of 17 over 6 times the sine of 8t plus this phase angle phi, 1.816. Okay. So these two representations of our solution are equivalent. So this first one up here is what we got from solving the ODE directly. The second one here is what we got from calculating the amplitude and the phase angle. Okay, they're both correct, but the second version here, this is physically clearer because it's involving the amplitude of the motion, so it directly relates to the motion of the spring. And the phase angle also tells you whereabouts in the cycle you are starting. Okay. Okay, great. So, well, we only covered case 1 in this lecture, so we'll move on to the next 3 cases in the following, the next 2 out of the 3 cases in the following class. Thank you very much.